Good morning. Welcome to the online video lecture on analog electronics. In the last class, we have discussed the block schematic of 555 timer. In today's class, we are going to focus on one of the specific application of 555 timer, namely monostable multivibrator. Before we step into monostable multivibrator application, let us try to understand the timer working. So the block schematic of timer is shown here. It has got three input signals, namely the trigger input, uh, reference input, a reset input, and we have one output which is shown here. And if you look at internal to this, there are three units: the charging unit, which is here, and the comparator and the output unit here. So the charging unit here shown here is associated with the RC circuit here, and this internal RC circuit has got trigger input here. So the trigger input is activated by pressing the switch here. It's basically a push button switch. Pressing this switch momentarily, the capacitor starts discharging. Once capacitor starts discharging through this path shown here via the switch, the voltage across capacitor becomes 0. So after releasing switch, the capacitor starts charging once again through the resistance R here. So therefore, overall charging time constant is the product of resistance and capacitance here. So this is going to be a time constant, charging time constant of capacitance. So VC is nothing but the voltage across capacitor is nothing but the input to the comparator here. So comparator compares the voltage which is coming here VC and the reference voltage. So based on this, the decisions is accordingly made. If the comparator voltage, if the VC capacitor voltage is greater than the reference voltage, then the comparator output goes to high level. So when the comparator output goes to high level, so output will stay at 0. So because this is output is straight away going to the S input here, and we take output here at Q bar. So therefore output goes to 0 here. Immediately after applying the trigger here, once we apply the trigger here, the capacitor starts discharging. Once capacitor starts discharging, voltage across capacitor VC that becomes 0. Once voltage becomes 0 here, VC will be less compared to the reference voltage. When VC is less, so output of comparator goes to 0. Once the output of comparator goes to 0, the output of this timer goes to 1 here. So this is how the basic block schematic of 555 timer works here. Now let us move on to the next circuit here, which is basic timing circuit here. So the basic timing circuit which is shown here uses RS flip-flop here. So initially, let's assume that the Q value is going to be 1 here. So once we assume Q value as 1, this Q is nothing but the input to the transistor Q1 here. So transistor Q1 goes to saturation. Once transistor Q1 goes to saturation here, the capacitor which is connected here finds path to discharge. So this is going to be the discharge path of capacitor. Once capacitor discharges, voltage across capacitor becomes 0. So this capacitor voltage is nothing but VC is nothing but the input to the comparator here, which is nothing but the threshold voltage here. That's a non-inverting. This VC goes straight away into the non-inverting terminal of the comparator. So that is nothing but the threshold voltage here. And if you observe here, there is a control voltage which is going straight away into the inverting input here. So now let us find the voltage across the resistance R2 here. The voltage across resistance R2 can be estimated by applying voltage division rule here. Since we know supply voltage equals 15 volts, here the resistance is going to be 10 kilo ohm. So we can use here this formula, voltage divided formula. So the control voltage is now supply voltage VCC times R2. R2 is nothing but 10 kilo ohm divided by sum of these two resistances, which is 5 plus 10 kilo ohm. So the control voltage is now as a constant value of 10 volts here. So here the voltage is going to be 10 volts. Okay, this is a constant voltage which exists here. So now high input is applied when we apply high input to the reset pin here. The Q becomes now 0. Q changes to 0 now. So once Q changes to 0, Q is nothing but the input to the Q1 transistor. So Q1 transistor will be turned off. Once Q1 transistor turns off here, so the capacitor is removed from the ground here. The capacitor will start charging via this resistor R. So the charging path is shown here. This is going to be the charging path here. So once the capacitor keeps the charging here, so the voltage at VC keeps rising. So voltage here keeps increasing. So once voltage here rises, once it rises above this, the 10 volts here. So the output of comparator goes high here. Once output goes to high here, so the corresponding Q becomes high here. Once Q becomes high, Q bar becomes low here. So this is how the working of this circuit can be understood here. So now let us see the waveforms here, how this waveform can be understood from this circuit diagram. Initially when the Q1 is on, so this is a Q1 transistor. When this is on, so the voltage, the capacitor voltage is going to be 0. So voltage, because the capacitor discharges, so the capacitor voltage is going to be 0 here. So now once now as you know, capacitor when the once the once the capacitor start the charging, once capacitor starts charging here through the resistance here, so we can see that capacitor is charging and voltage here start to build up. When voltage starts to build up here, once the voltage here at the threshold becomes greater than 10 volts here, so this output of comparator goes to high level and output goes to high. The Q becomes high and Q bar becomes low here. So during this pulse duration here, the capacitor is charging through the resistance R. Once capacitor voltage rises to 10 volts here, so the output the Q bar drops to 0 here. So during this period, during this pulse here, capacitor is charging. As long as capacitor is charging, the pulse width, the output will be a pulse of duration here T on. Okay. So once a capacitor reaches its voltage, say here 10 volts, once here voltage rises to 10 volts, output goes to high, and when once output goes to high, Q becomes 1 and Q bar becomes 0. The output of output here drops to 0 here. So these are the basic timing circuit works. So this block diagram we have seen in the last class also. So here we will just brush up the basic block diagram of triple five timer. So the basic block diagram of triple five timer contains a comparator 1 and comparator 2. There are two comparators here, and there is a resistance here. All resistance values are going to be a 5 kilo ohm resistances here. So that's why the name is a triple five timer here. Last class we have shown that how this voltage is 2 by 3 VCC. If you apply voltage division rule here, we can estimate the voltage at this point is 2 by 3 VCC, and voltage at this point is going to be 1 by 3 VCC. Now, depending on the threshold voltage and trigger input here, the output of comparator changes, and the output of comparator goes to the SR flip-flop. We already know the working of SR flip-flop. So accordingly the Q and Q bar changes here. The Q bar is the straightaway it goes to the output of it's an output of a triple five timer, whereas the Q goes to the transistor. This transistor is called as a discharge transistor. So whenever Q is 1, the capacitor connected here will discharge it through this transistor. When Q becomes 0, transistor QD will turn off, and so capacitor here will charge. So this we have seen in the previous circuit here. The whole circuit is has come with a package. This package is usually made by different companies here. One popular company is Signetic company. So their naming convention is NE555. So they put this complete circuit into the integrated circuit, and now 555 timer is available as a IC package with total number of pins is 8. So pin number 1 can be identified by the knob here, which you can see here. So on both the sides we can find equal number of pins. Pin number 1 is going to be the ground, which we have already seen here. Pin number 2 is going to be the trigger, which is here. Pin number 3 is the output pin, which is shown here. Pin number 4 is the reset. Reset is nothing but now we can apply here. This is usually the pin number 4. Pin number 5 is going to be the control voltage. We have already seen this control voltage is which is here. That is a pin number 5. Pin number 6 is going to be the threshold voltage, which is here. Pin number 7 is going to be the discharge pin. So we connect capacitor here, so that capacitor will find a path to discharge through this transistor. And finally we have a VCC to power up this 555 timer here. So VCC and ground, which are both are required to power up this 555 timer. Okay. So with this block diagram, so we'll proceed to the now operation of monostable multivibrator. So monostable multivibrator can be built from a 555 timer. So 555 timer is finds it has got plenty of applications. Among those applications, the the popular application is the monostable multivibrator. So the monostable multivibrator is built through this resistor and capacitor here. These are the main elements in this monostable operation. Monostable multivibrator is also called as one shot because it has got only one stable state. The other state is called as a quasi-stable state. So it remains always in a stable state. This is in this case stable state is low state here. It always remains in the stable state. So whenever we apply the trigger pulse here, it goes to the high state here and stays there for some time. That depends on the value of resistance and capacitance. That's a charging time constant. Once that time elapses, it comes back to the once again to the stable state. So in a summary, the monostable multivibrator has got only one stable state, that is nothing but low in this case. And as and when we apply the trigger pulse here, it changes its state from low to high, and this is only temporary. That's therefore this is called a quasi-stable state. And as I told you already, it depends on the resistance and capacitance. One that is once that time constant is elapsed, it will come back to the original state here. Okay, this uses the RS flip flop here. That's we already seen the 555 timer internal diagram. The same here, the internal diagram is retained here, but additional thing is we have one resistor and one capacitor. And here to operate this as in the monostable mode, we apply the trigger input here. Now let us assume that initially Q is in one state here, and let us try to understand this overall working of this. Since we assumed the Q as 1, Q bar will be in the 0. So we are here now. Okay, Q bar is 0 now. So Q straight away goes to the QD transistor here. That is the base of QD transistor. And now capacitor which is connected here finds a path to the ground. So in earlier cycle this capacitor might have charged fully. Now since capacitor finds a path, since this transistor is turned on here, so this is this transistor is turned on, so capacitor finds a path to discharge in this way. Okay, so for Q is equal to 1 state, this is the initially we assumed it, and Q bar will be low. So Q bar will be low, so QD goes to saturation. Once QD goes to saturation, so capacitor finds it paths to discharge. So therefore the once capacitor completely discharges here, so voltage across capacitor will be 0. Okay, so voltage across capacitor will be 0. So in this cycle the output stays at 3. Output stays at low. Output is nothing but the pin number 3. The same has been highlighted here. So the flip-flop is initially set with Q is equal to high. That's what we have seen here. This drives the transistor QD to the saturation. We have seen here this since high pulse comes here, this moves to the saturation. The capacitor discharges completely. The voltage across capacitor will disappear because it's connected to the ground here. It's nearly 0. So the output at pin number 3 stays at low. So this is what we have seen here now. Now let us see the second thing here. When a trigger pulse is applied here. So negative going trigger pulse is applied at pin number 2 here. So when a trigger input, a low going pulse is applied. This is what the low going pulse which we have shown here. And then circuit state remains unchanged till the trigger voltage is greater than 1 by 3 VCC. So when we apply negative trigger pulse here, as long as the pulse stays above this level, I mean this level here, so the output states doesn't change anyway here, thus it remains at 1 and 0 only. So therefore the pin number 3 stays at low. That's what we highlighted here. When a trigger input is applied, a low going pulse is applied, the circuit state remains unchanged till trigger voltage is greater than the 1 by 3 VCC. But now what happens when the trigger input goes less than this 1 by 3 VCC? We'll see that. So when it becomes less than 1 by 3 VCC, here the voltage trigger input drops less than 1 by 3 VCC. So already we know that here voltage existing voltage here is 1 by 3 VCC exists here. This is a constant voltage 1 by 3 VCC exists at this node, and at this node, you know, there is a 2 by 3 VCC exists here, and this is 2 by 3 VCC exists at here. So now here we applied negative pulse here, which is less than 1 by 3 VCC by 3. So already there is a VCC by 3 exists at is applied to the non-inverting terminal of the op amp. Since here triggering input drops less than 1 by 3 VCC, so this is less compared to this upper input here. So therefore reset input goes high. So this input goes high here. So once reset input goes here, the flip-flop will get reset. So reset means, so the output here changes to 0 here, and Q bar changes to 1 here. So you can see the flip-flop now changes its state, output changes its state from low to high the moment we apply the trigger here. Okay, so it stays at high now. So let us see that what the details of this. When it becomes less than 1 by 3 VCC, the comparator 2 goes to high. That's what we have seen here. Comparator 2 goes to high. This resets the flip-flop. So Q goes low. So Q goes low here, and Q bar goes high. Q bar is high now here. So low Q makes the transistor QD off. Now if you look back here, so the transistor low value of Q that makes transistor QD to turn off here. So this value, this transistor will be now, it is off, because we are getting Q as 0 here. Therefore this transistor turns off here. Once this transistor turns off here, the capacitor which is connected here will get disconnect from the ground. Now it starts charging via this supply. So the capacitor charging path is like this. It charges now. So this is the charging path of the capacitor. Hence capacitor starts charging through the resistance R, which is shown here in the the path is shown here. So the voltage across now capacitor builds slowly. It rises to a higher level. So voltage across capacitor increases exponentially. We know that voltage across capacitor is an exponential increase. This voltage is nothing but the threshold voltage at the pin number 6. So here this voltage across capacitor is nothing but the a threshold voltage that goes straight away into the non-inverting terminal of the comparator 1. The voltage at the non-inverting terminal of comparator 1 rises. Here the voltage is rising as capacitor keeps charging. Voltage rises here. Once the voltage here becomes greater than 2 by 3 VCC, already we have seen that here there is a 2 by 3 VCC exists, and now at pin number 6 our voltage across capacitor rises beyond the 2 by 3 VCC. Then the comparator 1 output goes to high. So that's what we have seen here. So when this voltage becomes more than 2 by 3 VCC, then the comparator 1 output goes to a high level here. So this sets the flip-flop. So now once the comparator comparator 1 output goes to high level, the flip-flop output is now set. Set means this becomes 1 now. It is set now. So this sets the flip-flop. So Q becomes high. Q we are seeing now it has become now high. because of the non-inverting input as raised here. So once Q becomes high here, so the Q becomes high here, Q bar becomes low here. So in turn the Q bar becomes low here. So we have entered into the normal mode now. So Q bar becomes low now. So this Q now, what we are seeing here, one that drives the transistor QD. So QD again it goes to the saturation, which you was saying in the previous case here. So QD goes to the saturation. Thus again capacitor quickly discharges through the QD here. So this is again the discharge path shown here. So it can be noted now at pin number 3. So in the beginning we have started with low level. Once a trigger pulse falls less than the VCC by 3, the output at pin number 3 rises to high level, and it this stayed at high level, once capacitor starts charging. Once it charges to the level of 2 by 3 VCC, so it again fall back to the normal state here. So this is how the monostable circuit works. Okay, so it again becomes low till next trigger pulse is applied here. So from this we are able to generate a rectangular wave. What you can see here is produced at the pin number 3. So this is a pulse of width, W we can see here. So this pulse width of this pulse depends on the resistance and capacitors here. So we can vary the width of this by changing the resistance and capacitors here. Okay. Now let us summarize this working, through this a summary. So here again we have taken the same circuit once again. Let us see the step number 1. In the initial stage, we have seen that we assumed that output is low. So we started with assuming output is low. So this is output here. So this is output is low. So Q is initial stage output is low. So Q is high and Q bar becomes Q bar becomes low. So we started with this is low here. So this is low here. Output is low. Q becomes 1 here. This is 1. Let's erase this one. So this is yeah. So this is Q is 1 and Q bar is low. So output we have taken assumed as a low here now. So QD becomes on since Q is directly connected to the transistor here. QD becomes on. So capacitor now discharges. So this is the discharge path we have shown here. So capacitor C gets discharged. So now once we apply the trigger pulse here, this is step number 2 in our operation, in our analysis. In step number 2, we are just applying a negative pulse here at the pin number 2. So trigger is applied with a trigger voltage less than 1 by 3 VCC. So let us see that what happens in step 3 once a trigger pulse is applied. So once trigger pulse is applied, if it falls less than VCC by 3, that makes reset input as 1. So here reset input becomes 1. So Q becomes a low. For this change, the Q becomes here low, and Q bar becomes now 1. This changes to 1. So we are seeing here high pulse here. So Q bar becomes 1 and QD in turn becomes off. Once this transistor becomes off here, capacitor gets a charge here. So we are seeing it output is high, output will be high, and capacitor starts charging to VCC. Though the trigger becomes 0 here, R and 0, R is equal to 0 and S is equal to 0. If you change the pulse here, there is no change in the output here. Okay, so it charges up to 2 by 3 VCC. Once voltage crosses 2 by 3 VCC, so what happens now? So VC, once it becomes equal to 2 by 3 VCC, that makes S as 1. So once S becomes 1, so R is 0. So Q becomes high now. Q is we return back to the original state, and Q bar becomes low. So we entered into the normal state here. So QD again it becomes on, and capacitor discharges to the 0 through the QD. So this is the overall. This explains the overall operation of a monostable using 555, a timer here. Okay, so here we can plot the waveform of this monostable operation here. The first waveform shows the trigger pulse applied. We can apply this periodically, this trigger pulse, but here we have shown just one pulse which is applied. So whenever the trigger pulse falls less than VCC by 3, then the changes are going to happen. So this last waveform shows the output at pin number 3, and usually the output stays at low. This is our stable state. So once a trigger pulse is applied at this timing instant, you can see that output changes to high level here. So capacitor keeps charging here. So once the capacitor starts building voltage, it reaches a 2 by 3 VCC. All of a sudden the output voltage drops to a normal state here. So here this is called as a quasi stable state. This high level state or quasi stable state or temporary state will not be for long duration. So it depends on the resistance and capacitors here. But stable state is zero for this monostable circuit. Okay. So this is the threshold or capacitor voltage waveform. The last waveform is going to be the output waveforms. So this shows the waveforms of monostable operation, waveforms of monostable operation using 555 timer here. Now it's very important for us to derive the expression for the pulse width. Usually in examination they will ask you the problems based on this pulse width here. Let us see that now the expression for the pulse width here. The voltage across capacitor, once it is charged, it increases exponentially. So therefore we can use this charging equation, voltage charging equation. Vc equals V times 1 minus exponential e to the power of minus t by c into r. If voltage across capacitor is 2 by 3 VCC, then we can see that if we apply this condition here, so 2 by 3 VCC is the voltage across capacitor, and this is supply voltage, which is VCC. So on simplification, so VCC cancels here. 2 by 3 minus this one can be transferred to the other side. That becomes 1 by 3 here. On right hand side we have e to the power of minus t by c into r. Now if we take log to the base e on both the sides, we have left out with right hand side with minus t by cr. Log to the base e of 1 by 3 is minus 1.0986. On simplification, this the final expression for the pulse width is t is equal to 1.0986 c into r. This can be approximated to 1.1 c into r, where c represents the capacitance in farads, r represents ohms, and t denotes the seconds. So thus we can say that voltage across capacitor will reach 2 by 3 VCC in approximately 1.1 times the product of resistance and capacitance here. So thus the pulse width is denoted as W, and W equals 1.1 RC now. So now previously we have shown the detailed circuit of monostable using 555 timer that can be written by just using the block diagram of our IC version of 555 timer. So this is the schematic diagram of a monostable multivibrator using 555 timer. So we can see here we have used just R and C as the external elements here, and so we have a capacitor here for discharging. So this overall circuit now is a compressed form of the circuit that we have discussed earlier here. So this is a schematic diagram of IC 555 circuits, which is shown here, which doesn't include the capacitors, flip flops. All those things are suppressed here. It only shows the external components such as resistance and capacitors, which are connected to the pin number 8 of 555 timer. So this schematic diagram of 555 timer works like a monostable multivibrator here. So the external components, resistance and capacitors, are shown here to avoid accidental reset of pin number 4 here, which is always connected to the short circuited with pin number 8, and that is in turn tied to the VCC. Because we know that the pin number 4 is reset here. So in order to avoid this accidental reset, this pin number 4 is tied to the high level. We know that the flip-flop used inside this 555 timer is active low. As long as we tie this pin number 4 to the high level, the flip-flop here does the normal operation. Okay. So that's the one thing. It is connected to supply voltage. To have the noise filtering of control voltage at pin number 5 is grounded via the capacitor called capacitor value 0.01 microfarad. Now we'll see once we understand the operation of 555 timer as a monostable multivibrator. Now let us take some design examples here. Design a monostable multivibrator for a pulse width of 10 millisecond. Here time is given as 10 millisecond, and using 555 timer, we are supposed to design a monostable multivibrator that generates a pulse width of 10 millisecond. Since in this problem W is given as 10 millisecond, we can use the formula that we have derived just now. W is equal to 1.1 RC. W is given as 10 millisecond, that can be substituted here, and which is equal to 1.1 RC. So since there are two variables are there, so one of this value can be assumed and other value can be calculated. So the RC product now it's equal to 9.0909 time into 10 to the power of minus 3. Let's assume capacitor value as 0.1 microfarad. So using this capacitor value in this equation, RC equation, we can obtain the resistance value. Resistance value is found to be 90.909 kilo ohm. This can be approximated to 91 kilo ohm here. So the circuit that is designed is shown here in this. So we have here 91 kilo ohm resistance and 0.1 microfarad capacitance. So here from this circuit, since supply voltage we have assumed as 15 volts, we are able to generate pulse width of 10 millisecond, which is given here. Okay. Now let us take another example to understand the working principle of a monostable multivibrator. Here the problem is we need to design a timer which should turn on the heater immediately after pressing a push button, and should hold the heater on state for 5 seconds here. In summary, we can explain problem like this. So here we have a circuit diagram. Uh, so here the user is pressing this trigger pulse. Once he presses here, so here we have an heater that should turn on for 5 seconds here. So we should generate a delay about 5 seconds here. Okay. So you are pressing this trigger pulse momentarily, but this in turn should generate a delay of heater should turn on for 5 seconds here. Now let us see that how to design this circuit here. So this is the best example for monostable multivibrator. So the time delay is given as 5 seconds here, which heater should turn on for 5 seconds when the user presses here the trigger button momentarily. So T on is 5 seconds here. So we can use same formula, W equals 1.1 RC. W is given as 5 seconds here, which is equal to 1.1 RC. Now there are two unknowns are there, as we have assumed in the previous problem. Capacitor value can be assumed and resistance value can be calculated. If I assume capacitor value as 10 microfarad, so if we substitute here in this equation, so resistance value can be calculated. So we know that we found that value of resistance is 545 ohm resistance. Though this is not a standard value, we can use a potentiometer of 454 kilo in that range, and we can adjust the resistance value to this value. Okay. So once we estimate resistance value by assuming the capacitance value here, we can design the monostable multivibrator. So we have a resistance which is given here, which we have designed here, capacitance which we have assumed. If you substitute these two values now, now if user presses the trigger button momentarily, this circuit will turn on this heater for 5 seconds. So delay what we get here is for 5 seconds. Here the pulse will go for high level here. Once 5 seconds is completed, the output will go for a low level here. So here output stays at high level for just for 5 seconds. For remaining time it stays at 0 here. Okay. So we are today this completes today's class, and in a nutshell, if you want to summarize, we have started with a introduction of timer. We have seen the basic timer, how it works. Then we've explained the internal block diagram of a 555 timer with the pin diagram, and we have built an application called as monostable multivibrator. Is a very popular application of a 555 timer. So we understood the monostable multivibrator through the examples here now. So that completes the design aspects of monostable multivibrator. In the next class, we are going to study the another application of triple five timer, namely stable multivibrator. Stable multivibrator is called as a free running multivibrator. Just in the monostable multivibrator we have seen, uh, there are two states, of course. One is a stable state, other one is quasi-stable state. So whenever the trigger pulse is applied in monostable multivibrator case, it moves to the quasi-stable state and stays temporarily there for certain duration of time, and comes back to the original stable state. So without applying trigger, the monostable multivibrator doesn't change its state. So trigger pulse is compulsorily required for the monostable multivibrator to change its state. Whereas in case of astable multivibrator, the both the states, it has got two states and both are temporary states. It keep oscillating between the two quasi-stable states. So therefore the astable multivibrator is also called as a free running multivibrator. So we'll take up the astable multivibrator in the next class. So we end up today's class. I want to thank you all of you for watching this online video.